and then in the transition zone it goes up, and then for the turbulent flow you can see that it decreases here. So this local friction coefficient, which we will be using to calculate the friction drag forces or surface friction forces, clear skin friction forces. So you can see it's not constant, it is variable. You see here for the laminar, and it is variable with respect to this x. So if we have laminar layer, then for laminar layer you can use this equation to calculate the local friction coefficient. Why local? It is at a distance x, and you will calculate the Reynolds number at a distance x. So we can calculate at any point. For example, you want to calculate here at this, for example, we have this x1. So what is CFX1? Similarly at this point here, so let's say this is x2, and so on. So this we can calculate at any distance x. This equation you can use. If we have boundary layer turbulent, then in that case the local friction coefficient can be calculated using this expression, where Rx is the local Reynolds number. So this is how we can calculate this friction coefficient, and you can see that it is variable, changing. This is the diagram which is shown here. But sometimes, for example, we have only this situation. Let's say this is the problem given to us, that we have only laminar boundary layer, and for this you want to calculate the friction drag force. So then in that case, which CFX you have to put? So instead of, you see it is variable, we just go for the average conditions. Clear? Now Rx is the local Reynolds number. So this is equal to rho Vx by mu or Vx by nu. We already know about this. The laminar boundary layer, to calculate the thickness of the boundary layer, so this is the formula that we can use. Delta by x is equal to 4.91 divided by square root of Rx. So at any distance x, you calculate Rx, and then we can calculate the thickness of the boundary layer. Similarly, if we want to calculate the shear stress, so that is denoted by tau naught or tau W, the wall shear stress, or tau naught. So it is given by this equation here. You see the shear stress is inversely proportional to x, and as the x increases, the shear stress is expected to decrease. Similarly, the friction coefficient that we can calculate for the laminar boundary layer by this equation. CFX is equal to 1.328 into square root of R. So this we will be for the entire length L that we want to calculate, whereas this one, this is for any distance x. You want to calculate the friction coefficient for laminar layer, but that is for the entire length. When we have R, it is for the entire length L. This is the coefficient. Clear? Similarly, if we have the turbulent boundary layer, so then in that case, this equation we can use to calculate the thickness of boundary layer, delta. And this is the expression for the shear stress. Now in case of turbulent boundary layer, when R is greater than 500,000 and less than 10 power 7, you can use this equation here to calculate the friction coefficient. If R is greater than 10.7, then in that case we can use this equation to calculate the friction coefficient. So this equation was given by Schlichting, clear, an engineer, Schlichting. he gave this equation, and you will see that even for r less than 10 power 7, still if you use this equation, this will give values very close to this equation. So that's why commonly engineers, they use this equation commonly for the entire range of turbulent boundary layer. This is written in your textbook. And if we have a transition at RC is equal to 500,000, if we have a regime of transition regime exist, then in that case CF will be calculated using this equation. So this is essentially, you see here, this is essentially here with just this addition factor minus 1700 by R. So you will see in the problem that even for transition regime, if you use this equation, it will give very close answer to this equation. But anyhow, for specific conditions, we can use these equations, and these equations are derived if you see your textbook, but we will not go into derivation at this stage. Just understanding of these equations and how to apply them to solve problems is most important. So that's why we are not going into complex derivations, but these can be derived. Clear? We have different theories that exist for that. Now in this diagram, we have a comparison of the friction coefficients for the different regimes. So you can see here for laminar regime, this equation, it gives this line here. Then for the transition regime, this curve is here. And for turbulent regime, we have this equation that we just discussed. You can see this is the comparison of the three regimes, the friction coefficient with respect to the Reynolds number. Next, we studied about what is boundary layer, how it develops. We study its development for a flat plate, then the laminar boundary layer, the turbulent boundary layer, and the different equations that we can use to calculate the thickness of boundary layer, the shear stress, and the friction coefficients. Clear? Next important topic is boundary layer separation. So what is boundary layer separation? First, we will try to learn what is boundary layer separation. Then we will study that what is the mechanics that boundary layer is separated from the surface of the body, and what can be the disadvantage of this. So you can see here that when we have a curved surface, then you see due to the boundary layer development, we have this velocity gradient. You can see here the velocity gradient that is developed, but outside the velocity is undisturbed. You can see here the velocity is undisturbed outside the boundary layer. So this boundary layer, it stick to the surface, but you see when the fluid reaches point S, after this the fluid follows this line. The fluid follows this line rather than it continue to follow this blue line. So it means that the boundary layer gets separated, clear, from the surface of the body. So this is known as boundary layer separation. And this S is the separation point. And you can see that because of boundary layer separation, there are eddies created. Recirculation flow has generated. So what does it mean? It means that because of this regeneration or recirculation of flow, it will increase the drag force on the body. So that's why it means that this boundary layer separation is undesirable phenomena. Because if boundary layer separates, it will increase the drag force on the body, whereas our purpose is to reduce the drag force. So this phenomena in which the boundary layer gets separated from the surface of a body This is known as boundary layer separation. And now we will learn that why boundary layer separation takes place, and then how we can avoid or minimize this phenomena so as to reduce the drag force. To understand this, you can see here that a fluid flow occur past this object. You see that at this point, these are the streamlines which are shown here. Now at this point, if I exaggerate this point here, this is what is shown here, that the boundary layer, it should follow this path. It should continue to follow this path. But instead of following this path, it follows this path. Means that it has separated from this surface. So that's why this is the point of separation, and this point, this fluid will go here. If we have another line, it will follow this direction, and so on. If we have another fluid here, it will follow this direction. So it means it has separated from the surface, and this recirculation of flow will occur. This is what you see here, recirculation of flows. And this wake is developed. So this is the separation point here, which is shown here, this S. This is boundary layer separation. What is the effect of this? That because of the boundary layer separation, the average pressure on the rear half of the cylinder here at the rear half is considerably less than that on the front half. Thus, a large pressure drag is developed, even though the viscous shear drag may be quite small. So it means that when boundary layer separation takes place, it will result into large drag force. It will result into large drag force. So this is the boundary layer separation concept. You can see the flow past this object here. You can see here this flow which is shown here. Flow past an ellipse. So you see that the point has separated here. See? Separation has taken place here. So what will be the effect of this? The drag force will increase on the body. So now this is the concept of boundary layer separation. That what is boundary layer separation? Next we will study what is the mechanics behind this boundary layer separation, and then we will study how we can avoid or minimize this boundary layer separation in order to reduce the drag force on the body. You can see here, before I explain this figure, you can see the effect of shape on this boundary layer separation. Now in this case you see that the flow occurs, but the shape is very similar to that of a flat plate that we studied earlier. So you see there is no separation on the top surface as well as at the bottom surface. There is no separation. Clear? But if we change the shape and the body is a curve, you can see here that separation point and boundary layer has separated here. You can see here recirculation will occur. And what will be the effect of this? The drag force will be increased on this body. But if you streamline the body, see, the boundary layer separation can be avoided and you see that in this case the movement of the flat plate will be faster as compared to the other shapes that we saw in this video. So it means that when the body has a curved surface, more likely is the tendency for boundary layer separation. Because in case of flat plate, if you come here to the flat plate, you see there is no boundary layer separation here. Throughout the flat plate, the boundary layer sticks to the surface. So essentially, it means we are assuming the pressure gradient to be 0. Clear? When we have a curved surface of the body, as you can see here, then there can be a tendency that we have the boundary layer separation. So now let me explain what is the mechanics behind this boundary layer separation. This diagram is taken from another book, so that's why the velocity is denoted by capital U. So no need to change it to capital V, but you should understand that this is the velocity, du by dy. Just to be consistent what you are using, clear? For Newton's law of viscosity, mu into du by dy. So that's why I leave this velocity as u and did not change it to v. Now in this case, what is happening is that the flow is occurring around this body. So now from A to B the flow occurs. This is point A and this is point B, the flow occurs. The boundary layer develops. This is the boundary layer. The top surface of the boundary layer. This is the top surface of the boundary layer. Outside this layer, the fluid is undisturbed. That's why you see the vectors, they are equal magnitude. And inside, we have this velocity gradient. Now at this point, the boundary layer separates and it moves in this direction rather than following the surface. You see up to here, the boundary layer is stick to the surface. But at C point, it separates from the surface and it flows like this. And you see here that we have a recirculation, which you saw in the video also, in the previous figure also. This recirculation will occur. Now that we understand up to this point, so what we see here is that when the fluid moves from A to B, you can see here that the pressure gradient is negative. It means that we are moving from high pressure. What we have here is we have high pressure. And at this point, what we have low pressure, which you can see here even from this diagram. The low pressure here, the minimum pressure X here, low pressure. So we are moving from higher pressure to low pressure. So this is known as favorable gradient. This is known as favorable gradient because from high pressure to low pressure we move. It is favorable gradient. Clear? In this case, dP by dx is less than 0 because we move from high pressure to low pressure. So the velocity gradient, that is greater than 0. This is what you can see here. It is greater than 0. Now after this point B, and in here you can see that now onward from here we are moving to high pressure. You see from this curve, high pressure. So that's why dP by dx is greater than 0. Means we are moving from low pressure to high pressure. It means now we are moving from low pressure to high pressure. As the flow moves on this surface of the body, we are moving from high pressure, low pressure to high pressure. When you move from low pressure to high pressure, it means this is known as adverse gradient. This is known as adverse pressure gradient because we are moving from low pressure to high pressure. So what will be the effect of that? That in case of favorable gradient here, this is favorable gradient. This is favorable gradient from high pressure to low pressure. You see that the pressure, it is pushing this velocity in this direction, high pressure to low pressure. So the pressure is pushing this velocity in this direction. But when we move from low pressure to high pressure, it means the pressure is pushing this velocity in opposite direction because we are moving against the high pressure. So that's why you see it is pushing this velocity gradient in this direction, That's why you can see here it is moving in this direction. Because we move from low pressure to high pressure, so the high pressure is moving in this direction. So that's why you see the velocity is reduced. So at this point C, what will be the velocity gradient? 0. It is reduced to 0 from positive to 0 because of moving from low pressure to high pressure. So on further pushing, because we are moving from low pressure to high pressure, on further pushing, what will happen? The velocity gradient has become negative. du by dy is less than 0. You can see here, that's why this is adverse pressure gradient. So due to this adverse pressure gradient, it is pushing this velocity here. Now what will happen? That now the fluid, because the velocity gradient is now negative, so it means that the fluid is now moving actually in this direction. So now that the fluid is moving in this direction, and for this B to C, it is moving in this direction. So now when this fluid reaches here, point C, and this fluid reaches here, it cannot go here because we have solid body. So it cannot go here. What will happen? It will try to move in this direction. This is the separation point. And any fluid which is coming here will now move in this direction. Any fluid which is coming here will now move in this direction. And it will follow this curve path here. Because the fluid coming here and here, they have to leave the surface. So this is how the separation point is developed. So because of this separation point here, you see that there will be recirculation here. And after this point here, all the streamlines, they will move in this direction. So this is the recirculation that will be developed here, which you saw in the video also. So this is how the boundary layer separation takes place. This is the mechanics behind the boundary layer separation. Now we can conduct an experiment in which we can observe this boundary layer separation. We already saw a video, but Prandtl, he conducted a simple experiment to visualize the boundary layer separation. This is, for example, a cylindrical object, clear, or a sphere. Let's say a cylindrical object, and the fluid is flowing past this object with a velocity v. You can see here that at low velocity, the stream lines, they follow this path. But if you increase the velocity, so what Prandtl did in the experiment is that he put a cylinder here, and the fluid is allowed to flow past this cylinder. And to visualize these streamlines, he put he sprinkled particles of aluminum, because aluminum will reflect the light and the streamlines can be visible. On increasing velocity, he observed that these vortices form at the rear side of the cylinder at point D. You can see here. And if you further increase velocity, then these vortices become more and more prominent. You can see here. And you see that from D, these vortices have shifted towards A and B. So this was a simple experiment conducted to visualize the boundary layer separation. Now we know that what is boundary layer separation, what are the mechanics behind this. So the separation of boundary layer in turbulent flow may be prevented in order to have reduced drag. Many methods have been suggested. We will study only two methods. Clear? So the first method is by providing slots near leading edge. What will happen is that you can see here, when this flow occurs past this object, let's say airfoil, you see that boundary layer has separated and it will increase the drag force. You earlier saw in the video also. But if we provide a slot holes here in the entire length of this body, you can see here that the body is such that you see by providing these slots, the boundary layer separation is avoided. So this is one of the methods that we can avoid the boundary layer separation, because boundary layer separation, it increases the drag force. And this is what we can observe and done in aeroplane wings. For example, we have slates and flaps. This is a slate, clear, and this is flaps that are provided on the wings of aeroplane. So in this case, what happens during climb, you see that because of these slots and slates that are provided, the boundary layer will not be separated from the surface. You can see here by allowing these fluid to pass here, and it will reduce the drag force. And then during the normal cruising, the shape is like this. So you might have seen that during the landing of aeroplane, these flaps, they are extended down. You can see here, these are extended down. And these are spoilers. They move up. The reason is that in this pushing these flaps down will increase the drag force. And this is what we want during landing of the aeroplane, that we want to increase the drag force so that the aeroplane can stop as soon as possible. And these flaps are up because the air will come and it will move in the upward direction. They will move the air, push the air in the upward direction. So this will help reduce the lift force acting on the plane wings. So this is how you commonly have seen or observed this situation while landing the airplane. To just highlight this, you can see that we have the flaps. These are the flaps. These are the spoilers, red color, and we have the slates. So during climbing, cruise, and descent, clear, we have clean configuration. We have this situation, and in this case, you see the drag force minimized because of cruising, and the lift force, you see the surface area is more. Characteristic area that we can calculate, the length is more and then multiply by the width, so the lift will be more and the aeroplane can fly high in the air. During takeoff and initial climb, you can see this will be the situations. So this air flows through these here, which we saw earlier, and it will avoid the boundary layer separation and it will reduce the drag force. So it will help the aeroplane to move upward in the air. So during takeoff, minimize the drag force. You see here, the air will flow here and it will avoid boundary layer separation to reduce the drag force. Similarly, before we land, approach to landing, the lift is still the same because aeroplane needs to fly. But we want to now increase the drag so that we now move down and the speed is reduced and the aeroplane is getting ready for the landing. So then in that case, you can see here that these slats, they are put down. These slats are put down. So you can see here that high drag will produce. See, the area for the drag force, that is reduced, increased. You can see here the area for the drag force is increased. So that's why it will result into a high drag. Slow down the aeroplane and prepare for landing. And when it is landing, then you can see that this air flows here to avoid boundary layer separation, which is undesirable. These spoilers are raised, clear, so that the air, it flows up rather than in the downward direction. This is avoided. When this is avoided and the aeroplane, this air moves on the aeroplane wing upward, it will reduce the drag. See, reduce the drag, because now we are landing, we don't need to move upward. So that's why this will reduce the drag. And the flaps are down, this will increase maximum drag. So during landing, these flaps are extended down and spoilers are moved up. It will result into reduced lift and maximum drag. And this is what we observe during landing. When the aeroplane lands, you see the spoilers, they are moved up. These are spoilers. To minimize the lift force, we don't need to move up. And the flaps are moved down, extended down to increase the drag force so that the aeroplane can stop as much as possible in a short time. Now you can see here that when we have this situation, clean, no flaps, with angle of attack, the lift coefficient is 1.52. So when the lift coefficient is small will be the lift force. But if we provide double slotted flaps here, you can see that the lift coefficient has increased from 1.52 to 3.48. It means that for this situation of the wings, the lift force will be more because the lift coefficient is more. But for clean, no flaps, the lift force will be less. Less is the lift coefficient. Now that we want to increase the lift force so that the aeroplane can fly high in the air, we change to this. But there is a disadvantage. Why? Because you can see for no flaps, the drag coefficient is here. Let's say 0.06. But when you provide a double slotted flap, the lift force is maximized. But you can see here that the drag force is also increased on the aeroplane from 0.06 to more than 0.25. So then in this case, what will happen for this situation? The engine has to use more power to push the aeroplane in the forward direction. So anyhow, this discussion is sufficient for the lift force and the lift coefficients. We are not studying aeronautical engineering. They can go into more detail and see and study the physics of these concepts. But anyhow, this much discussion is sufficient for our basic understanding. So we studied first by providing slots. So the second method is rotating cylinder as leading edge. The second method. So what we see here is that we have a cylinder. When the fluid flows past this cylinder, you see here boundary layer separation. If we rotate this cylinder, then you can see that this wake is reduced. Boundary layer separation is minimized. So this can be a method to prevent the boundary layer separation by rotating cylinder. Clear? So these are the two methods that we studied. If you want to study more methods, you can study books on aerodynamics. Clear? Even a book which is available in our library, Hydraulics and Fluid Mechanics by E.H. Leavitt, a British book. So if you study that book, he has explained more methods on prevention of boundary layer separation. But anyhow, these two methods are sufficient just to get some idea that how we can minimize or prevent boundary layer separation. It is undesirable. Now coming to this case here, that when we rotate a cylinder, it can help to minimize or prevent the boundary layer separation. Then this concept gives rise to a very interesting phenomenon, which is known as the Magnus effect. What is the Magnus effect? It says that if we have this cylindrical body and it is rotated in a moving fluid, you see the fluid is moving past this object, and when it is rotated, you see at the top of this cylinder, these vectors are in the same direction. So it means that the velocity will increase in this direction at the top. And because at the bottom you see these vectors are in opposite direction. So it means you see the streamlines are further apart, the velocity is less at the bottom. Just like we observe when I explain the lift force concept. So it means that when we have a cylindrical body, can be a sphere also, no problem. When it is rotated in and also moving in a fluid, so at the top the velocity is increased and at the bottom velocity is decreased. So we earlier studied beginning of this lecture that this will give rise to pressure difference, and thus there will be high pressure here and there will be low pressure here, and this will result in development of a net force in this direction, which we earlier classified as the lift force. So this effect is known as Magnus effect. Clear? And this Magnus effect, generation of sidewise force on a spinning cylinder or spherical solid immersed in a fluid, liquid or gas, when there is a relative motion between the spinning body and the fluid. So when the body is rotating and it is also moving through the fluid, this Magnus effect can be observed. And this Magnus effect is responsible for the curved path of the tennis ball, driven golf ball, and the trajectory of the spinning artillery shell. So when you hit the ball and the ball is spinning, it is moving through the air, it will follow a curved path. This is due to this effect which is known as Magnus effect. Clear? It was observed by Magnus, so that's why it is named after him. So the phenomena of producing lift by rotation of a solid body is called the Magnus effect. You can see here we are assuming idealized flow, no friction, so that's why there is no boundary layer separation. Idealized flow flowing past this stationary cylinder. So you see the streamlines, they follow like this. Now the fluid is ideal, so that's why streamline closely follow like this. When this cylinder is rotated, so you can see here we have high velocity at the top because the vectors add up at the top. This will result into low pressure, and at the bottom we have low velocity and it will have a high pressure. That's why a net upward force will be developed in this case. If we have high pressure up, low pressure down, then a downward force will be generated. So it's not that it is always up. Remember this. So this force explains the curve path that is followed when you hit a ball and it is rotating. So again, this concept will be developed. You can see here now the fluid is moving in this direction, the ball is spinning in clockwise. So due to this, the Magnus force will be acting down on this ball. And this is what happens. You might have seen that in the soccer, football, when the fielder, when he kicks the ball into the goal post, you see the curve path is followed. This is due to this Magnus force. If it is rotating and moving through the air, it will follow this curve path. So that's why to move the ball in a curve path and put the ball in the goal post, this will be the expertise of the fielder. The more you are expert to do it, you will be successful in goals. So that's why we have experts for this in soccer. For example, you have heard the name Roberto Carlos. So this is the technique that he uses because of this Magnus effect to follow a curve path. And you can see here the goalkeeper has no absolute idea because he will think the ball will come straight. So this is a technique which is used for goals. Clear? This is due to this Magnus effect. To continue with that Magnus effect, clear? Flettner, he come in the 1920s with the idea. He was a German and then he worked in the US Navy. He come up with the idea that if we have a large rotors in the form of cylindrical shape, and if a wind is blowing and also the rotors are rotated, a thrust will be generated and it will push the body in the forward direction. For example, these are here. You see that these rotors are provided in the ship, and if these are rotated and the wind is blowing across the ship, it will push the ship in the forward direction. So it can be economical rather than we use engine and use fuel to push these large ships, boats, etc. We can use this concept, wind is blowing, and this was known as Flettner rotor. And because of this Magnus effect, it can produce a thrust, clear? Thrust, which will push this ship here, sea ship, in the forward direction. So this idea, based on this idea, these large ships were developed in the 1920s. In the shipbuilding, this idea was used. That rotor ships use these cylinders for propulsion, but it will require the wind. If wind is blowing and we rotate these rotors, it can produce a thrust on this large vessel or a boat or this ship, clear? So in this case, it will push it and it can be economical, clear? But this idea which was used and ships were developed, sea ships, and these ships made successful sails in the Atlantic Ocean. But then eventually this idea was given up because, number one, if there is no wind, it will not work. And the second thing, it was found that because you have to rotate these large rotors and still it needs the wind to work, so it was found to be uneconomical. So that's why this idea was not pursued. Although it was a successful story, but it was found that it was uneconomical. You can see a footnote in your textbook, it is written. We can even observe this phenomena and do an experiment here. You can see so we have this small boat, and now you see here that we have two small rotors that are provided, and the air is flowing across by this fan. You see it moves in the forward direction. So you can see that because of this Magnus effect, the small boat you saw in the video was moving in the forward direction, but this idea was not pursued after the 1920s because it was found to be uneconomical. Now in this case you can see that we have these bodies, so a sphere moving through the water, and in this case the drag coefficient, that is 0.4. Why? Because you can see the boundary layer separation, the thick wake that is created, and you see that the drag force is more. Now what we can do is that in this experiment here, if the front of this ball is artificially roughened, it is rough, so from smooth to rough, what happens that it will aid, this aided roughness and turbulent boundary layer cause increase in friction drag, because this is smooth, this is rough, you are making it rough, but you can see the shifting of the wake, it has shifted back. So it is written that although we are making the surface rough, we are increasing the friction drag, but this becomes secondary importance if we compare the marked decrease in the size and wake of effect of this wake. You can see here the effect and size of the wake, and then in here, so it has shifted from here to here. So of course this will increase the friction, but you see that this is the most important thing that has occurred. So that's why as a result this drag coefficient is reduced to 0.2 as compared to 0.4. So you can see that as compared to smooth, with roughing the surface of this body will move faster through the water as compared to this body. Clear? Similarly, you can see here that by providing a tripwire to induce transition to turbulent, so you see for this laminar separation here, you can see here separation is here, but for turbulent then separation is here. So that's why by making the boundary layer turbulent from laminar, it can move faster, or the drag force can be reduced. You can see here when a smooth ball is moving, so this is the wake, thick wake is generated. But in case of dimpled ball, you have a small depression. You see we have made the wake thin. So this is the main reason why the golf ball is dimpled. It is not smooth. If you have played a golf, you will see that the ball is not smooth. This is the reason. Because by smooth ball, it has thick wake. And by roughing the surface in the form of these dimples or depressions, the wake is made thin. So that's why when you hit a golf ball, it will travel more distance if the ball is smooth. As compared to smooth sphere, the golf ball will travel more distance. This is the reason why the golf ball is like this and it is not smooth, because this will travel more distance. As you can see, we have reduced drag forces in here. You can see here, compare the wake, the turbulent boundary layer for a golf ball, and if we have smooth ball, you can see here the wake is thick. So that's why this ball will travel faster because of reduced drag force acting on this as compared to this lower ball. This is the reason why the golf ball is dimpled. It is not smooth, because dimpled golf ball will travel and cover more distance. Similarly, this diagram is in your textbook, that we have this motor vehicle and we studied streamlining of the vehicles earlier. So in that case, you see that if the body shape is blunt, you see blunt nose. So this is the boundary layer separation, and a thick wake will be created here. You see here. And what is the drag coefficient? 0.75. But if we streamline the body, you see for a round nose, then this point of separation is shifted back. You see the size of the wake is reduced. So what is the effect? That the drag coefficient is 0.45. So that's why this vehicle will travel faster as compared to this vehicle for the same power. This is what we studied earlier in the previous chapter, streamlining of the cars. And we studied a graph there over the years. We are streamlining the shape to reduce the drag forces on the cars so that the mile coverage is increased. Now next we solve our problems. So we have this problem 9.4 from the textbook. To calculate the shear stress and the thickness of the boundary layer at the center and at the trailing edge of a smooth flat plate that is 10 foot wide and 2 feet parallel to the flow, immersed in 60 °F water flowing in undisturbed velocity of 3 foot per second. Assume a laminar layer over the whole surface, and part C is find the total friction drag on one side of the plate. So we need to calculate the shear stress and the thickness of boundary layer at the center and at the trailing edge of the smooth flat plate. So for this case, table A1 in the book, for this temperature you need to read the fluid properties. And we studied at the center of the plate. Plate is how much? 2 feet parallel to the flow. So that's why center of the plate will be 1 foot. This is Rx, the local Reynolds number, and X is 1. You calculate this. It is less than 500,000. It is less than 500,000. So what we have? It means that the assumption of laminar boundary layer is correct. So that's why R is less than that, and we have laminar boundary layer. And this is the equation that we discussed to calculate the thickness of boundary layer at a distance x when we have laminar boundary layer. So you can calculate the thickness. And this is the equation to calculate the shear stress in case of laminar flow, laminar boundary layer at a distance x. When you have Rx, it means at a distance x. So this is the value for the shear stress. Second is part B is at the trailing edge. Trailing edge means end of the plate, 2 feet. So when we have 2 feet, you can see that this is thickness will be more. As you earlier saw, when the distance increases, thickness increases. What happens to shear stress? Decreases, because you can see shear stress and X inversely related. So for the trailing edge, X is equal to 2 feet, Rx will be equal to this, and then you can use this to calculate the thickness of the boundary layer. You can see more than the previous case, and the shear stress we can calculate using this expression. So shear stress is less as compared to the previous one. Now drag on one side of the plate. Since we have laminar boundary layer, so CF you can calculate for this. This is for the entire plate, so that's why not X but R. Not CFX but CF, not RX but R, because for the entire plate now. So you can calculate the friction coefficient. And this is the formula to calculate the friction force that we earlier discussed. And this BL is the characteristic area A. This is the characteristic area A. We have a flat plate, so 10 into 2. This is the characteristic area. So this is how we calculate the friction drag force on one side of the plate. Remember, this equation gives the friction drag force on one side of the plate. This is, let's say, a flat plate. So this is FF. If you are asked in the problem what is the total friction drag force, then it will be sum of these two. So just on one side we want to calculate, or the other side it will be 2 times of that. That's why it is say the total friction drag on one side of the plate. Another is problem 9.9. An 85-meter streamlined train has these dimensions. Compute the power required to overcome the skin friction drag when the train is traveling at 40 meters per second through standard atmosphere at sea level, assuming the drag on one side, on the sides and top of the train to be equal to that on one side of a flat plate 7.5 meter wide and 85 meter long. It means that if we can calculate the drag force or friction drag force on this flat plate, it will be equivalent to that on acting on a train. So for the sea level, table A3 for the air, these are the properties you can pick from table A3 in the appendix of the book. Now we calculate R. R is 2.3 into 10 power 8. So greater than 500,000. So what we have is that we have turbulent conditions. So now use this equation. When R is greater than 10 power 7, we have this expression for turbulent flows, and CF we can calculate here. And then this is the characteristic area BL, 7.5 into 25 meter. This is the friction force. So this is equivalent to acting on a train. We calculated for a flat plate, and this is equal to that acting on a train. And then we know that power is equal to F into V, force into velocity. So power will be equal to force into velocity. This is the power required. Compute the power required to overcome the skin friction drag. And last problem, 9.2 from the textbook. A 20 millimeter diameter harpoon, 1.8 meter long with a sharp tip. This is a sharp tip, and this is the shape with a diameter. Diameter is given 20 millimeter with a sharp tip. This is like a missile. So it is launched at 6 meters per second, 15 degrees sea water. Find the friction drag and the maximum thickness of the boundary layer. So first we need to determine the fluid properties for the given temperature of water. Then we see that if a transition regime exists, so we want to calculate XC. It is now 0.0949. It means the total length is 1.8 meter. But the critical distance is 0.094 meter. So it means that transition regime exists. Clear? So transition region must exist. So that's why to calculate now the Reynolds number for L, it is 9.48 into 10 power 6. And for the transition region, we use this equation here. This is what we studied for transition. We calculate the friction coefficient. Even if you use the Reynolds number and you skip this one, still you will get the value very close to this one. So you use the turbulent flow or this equation, approximately you will get very close answer. But if you want to be very accurate, then you can use this concept. And then f of f will be equal to this, the equation there, but this is the characteristic area here. Since we do not have flat plate, this is the characteristic area. So instead of BL, we can write down here A, the characteristic area A. And what is the A? For the friction, it will be pi d into L. So this will be equal to pi d into L, because this is the friction that we want to calculate on the surface. Circumference into length, pi d. This is now the characteristic area. So this is the friction, and the second thing is the maximum thickness of boundary layer. So we already know that the thickness of boundary layer increases with the x. So that's why the maximum thickness will be at this point here, at the trailing edge. Clear? So that's why you put the entire length L, 1.8 meter. So in that case, X is 1.8 meter. This X is 1.8 meter. Because we already saw that as the distance increases, thickness of boundary layer increases. It is directly proportional to this. So this is the maximum thickness of the boundary layer. This is how we use these equations to solve the problems in this chapter.